Okay, we are a little bit past the top of the hour here, and we've got folks trickling in, so we'll go ahead and get started. You're in the right place for another RNG Coalition Wednesday webinar, and the second one this year featuring Bright Renewables. Very excited to have a returning presenter here today. For those of you who may not know me, my name is Dylan Chase. I'm Senior Manager of Communications for RNG Coalition, and if it's your first Wednesday webinar, this is where we really hold a forum to discuss the advancements that are helping to drive the massive growth in renewable natural gas and green gas that we've seen in North America in recent years, including developments that are technological or policy or educational or whatever it may be. We were joined earlier this summer by our friends from Bright Renewables to focus on biogenic CO2. That was a bit of an overview, and today we're going to get to dig a little bit deeper on the technology. And to that end, we're going to be joined by Perry Groves and Alir Tahiri. So welcome both of you back. Great to have you. And with that, I will hand over. But before I do, I'll just encourage all of our attendees to be sure to leave any questions or thoughts that you have in the Q&A window rather than the chat for our presenters' benefits. I hope you come armed with questions on the technology you're going to learn about today. And I'll also tease before I hand over that we're going to be having a part three in this series at some point coming up, a little bit even deeper of a dive on this subject. So with that, I'll hand over Perry. I think are you betting lead off today?
Yeah, that's right. And thank you for
Right.
the warm introduction, Dylan. It's great to be back on the Wednesday webinar series. And yeah, this is part two of our trilogy of webinars we're presenting on the CO2 aspects of these RNG plants. So this one will focus a little bit more on that technology, that technical aspects for CO2 and how we're monetizing that and how we can add value to our existing plants here. So just diving into at a high level what we'll be covering today. It would be good to start with a quick recap of the key takeaways from last time, just to give a quick refresh for those who attended there, and a nice little introduction and reminder for those of you who weren't able to make it the first time. We'll talk about the different technologies used to liquefy CO2 existing and what we see in our industry, as well as some of the considerations we need for cryogenic processes, which I'm kind of calling liquid CO2 101 here. Along with that, we'll talk about some of the logistical aspects, such as the storage and transportation, like you see on screen, and we'll round it out with how we actually integrate these CO2 plants into your overall RNG plants, or maybe another kind of plant, like a power generation plant. So just diving into this recap real quick, if you would like to watch the part one of the webinar, of course, this is available on the RNG Coalition's Wednesday webinar website, where all the recordings are. We also have it on our website, bright-renewables.com. You can see hitting the news section there, and that featured news, the first one right there, has that recording of the part one if you wanted a quick refresh, or if you weren't able to attend that first time there. We'll also have this recording on that website as well once we have it available. So you'll be able to see both parts on both the Wednesday webinar series website on the RNG Coalition, as well as Bright Renewables website. But just to touch on the key takeaways from part one there, we wanted to start with how RNG fits in and how biogenic CO2 fits into RNG plants. So we kind of see here in a high level process of where that CO2 actually goes. You can see it starts as that atmospheric CO2 that's absorbed into some of the organic materials that we're all familiar with as our feedstocks. Of course, going into the digesters, landfills, whatever process that is to create that biogas, feeds into an RNG upgrader, as we see in the middle of the screen here, where you typically separate out the methane used for RNG and the CO2, which traditionally up to this point has been seen as a byproduct and typically vented to the atmosphere right now. So kind of closing that carbon cycle that we see. As we talk about adding CO2 liquefaction and integration into these RNG plants, see at a high level what this process actually looks like. And as an example, we're using our standard three-stage membrane upgrading technology in the gray box on the left of the screen there, which you can see has fairly standard for us pre-treatment, compression, and then the 3 stages of membranes to separate out the methane, the RNG as you see on screen, and the CO2 tail gas. From that point, the CO2 tail gas can feed into the CO2 liquefaction technology, which you can see on the right half of the screen in blue, starting with pre-treatment mainly as a police or a safety net in case there's any upstream upsets that cause some contaminants to come down. We then compress the CO2, increasing that pressure from typically what we see as ambient coming from a tail gas stream. At which point we'll also dry the CO2 in the next step. And then once that CO2 is compressed and dried, we can lead that into the real meat and potatoes of our system, which is the cryogenic distillation process, as you can see on stream. It feeds first into our condenser, which will actually liquefy that CO2, that gaseous CO2 coming from the dryers. And that liquid CO2 will drop down the cryogenic distillation column, as you can see on screen there, before landing in the bottom, which will be the reboiler. And now, of course, that reboiler is not just a tank, it is a reboiler. And so you will see that liquid CO2 is actually reboiled and gasified once again to add a reflux stream, which goes into the process of distillation, where you have vapor liquid transfer and mass transfer throughout the column there to effectively purify your 2 streams that you have. So this results in a high purity stream of liquid CO2 sitting in your reboiler, and then your contaminants or your non-condensable gases, as we see it listed on the PFD here, is going to be those gases flowing upward, countercurrent to the liquid falling downward in the column. And those can be released either to the atmosphere, or as we point out on screen here, this can also actually be recycled back to the source of this biogas to potentially capture some of the non-condensable gases such as methane slip that you might see in your CO2 tail gas. And then once the CO2 is liquefied from there, you can go into storage and go into more of a logistical process of how you want to market that and what your offtake agreement actually looks like. Typically, this is storage done with truck transportation to your offtaker facility. Now, in the last part, we also, at a high level, touched on the grades of CO2 that we see in the industry right now and what we would be able to produce and market from our biogas plants. So you can see roughly 4 grades that we call out here. Industrial grade typically has a lower value, lower purity. Of course, you'll see that for industrial uses. Maybe you'll see that in the cement manufacturing, for example, that can be used as a binding agent. Typically used as an ingredient for processes, chemical processes, whatever that may be. That differs from food grade, which we see next, a higher purity, which has a stronger value because it's more pure. And we see that this is a high value market for biogenic CO2, used, of course, in food manufacturing processes as their use case. That is somewhat similar to beverage grade, which is the next one there. Again, a 99.9% purity. We have the asterisk there because beverage grade does have some more requirements behind that we'll touch on later. But this has a very high value, but it does have some requirements associated with that. So to speak, some hoops you have to jump through in order to realize that high value, and not as relevant for our uses and our CO2 that we're talking about is lab grade, which is very difficult and costly to produce because of the extreme purity that's required for lab grade.
Barry, while we're on this slide, I've got a question in the Q&A. And just to make note of it now, feel free to put your questions into the Q&A while we're presenting. If there's something on a slide that you want to ask more about, we're happy to interrupt the flow and have an open discussion. This question is, how does grade of CO2 impact price? This is a pretty complex answer, and so I'll try to synthesize it briefly here, not taking too much away from that 3rd installment of this webinar series where we'll do a deep dive on commercializing the product, contracting, and the business case. Grade of CO2 impacts price to a pretty large extent, but in many cases, location is more important for price, as we'll discuss briefly later in this presentation and then also in the next one. The actual transportation of liquid CO2 adds a lot of cost to the consumer. And when you're selling CO2 into the private market, you're working on a cost offset type of business model. So really, there's a lot of value driven there. The other caveat I would like to make now is that, if you have an off-taker and a consumer that only needs industrial grade, in many cases, a CO2 producer would be required to produce CO2 compliant with food and beverage grade quality standards from a molecular standpoint, as a measure of protecting the fleet of the distributor that might be selling the CO2 into a greenhouse or as a welding gas, for instance. Their fleet will have to be accepting only that 99.9% pure CO2.
Yeah, that's a great point to bring up regarding those fleets and effectively standardization around a specific quality, which I'm sure in our industry we're all familiar with some of the RNG standards where each pipeline has their own specifications to comply against. You could almost see it in that regard, except for the fact that there's a little less variation in the different standards that you'll see where you'll have a beverage grade standard, for example, for that fleet. So everyone has to comply with that. Jumping into our next slide here, we're going to go a little bit more into the different technologies that you'll typically see in the market to actually liquefy CO2. The two we have listed on screen and generally the most widely viewed and seen throughout many industries is cryogenic distillation here on the left, which is the process flow diagram we covered in a couple slides ago. And you can also see multi-stage compression as another form of liquefying CO2. So we have some high-level pros and cons listed on the screen here. Typically for our industry, as we talk about biogenic CO2 at a high level, we will typically be driving towards a cryogenic distillation model for the large portion due to the second bullet point on the left that you'll see there, where the cryogenic distillation process inherently removes non-condensable contaminants such as methane, as I mentioned before. And so while you purify the CO2, you don't need an additional process to remove or purify that CO2 because the cryogenic distillation process inherently purifies that CO2, as I mentioned before. Because at the conditions that we discussed in the reboiler in that cryogenic distillation column, the methane isn't cold enough to reach a liquid phase, so that stays in a gaseous phase, as well as some other non-condensable gases as we touch on. Multi-stage compression at a high level is seen in different industries. For example, the brewery industry is somewhere that you'll see multi-stage compression and used there because you typically don't see those non-condensable gases needing to be removed, or you don't see that in your CO2 feed stream. So cryogenic distillation, just to sum this up, generally the most cost-effective option that we see for biogenic CO2 specifically as our use case.
Touching on that period, the question came in the chat, which tech is more CapEx intensive? And honestly, they're relatively comparable in a lot of cases, particularly for our industry. Doing purification and liquefaction in one step via cryogenic distillation is typically less CapEx intensive. But in industries and applications where cryogenic distillation wouldn't be required for quality concerns, multi-stage compression can have a very competitive business case, if not better, namely due to some systems being able to be entirely cooled with glycol only, where you do multiple stages of compression with cooling in between the stages, and then some final cooling to have your liquid. So as Perry mentioned, in the brewery space, that's quite common. In our space, due to the non-condensable contaminants inherent in the tail gas stream, cryogenic distillation would be required to reach that food and beverage molecular quality that we've talked about.
Yeah, thank you for bringing that up, Alir. And because we're touching on the different technologies here, I thought it would be good to take a step back on this next slide here and talk about the science behind what's actually happening when we're talking about liquefying CO2. So sorry to those of you who maybe didn't take this class in your university studies or whatever that is. So I'll try to be quick on this slide because I know this starts getting into the nitty-gritty of what's happening. But in general, for CO2, you can see we've marked what a tail gas typical stream looks like on the bottom right-hand portion of the graph here. That's typically what we see, or about what we see, are the conditions for the CO2 tail gas coming from RNG upgraders. We'll get into it a little bit later, how this can change and depending on the technology that you use. And of course, every site is different, but in general, atmospheric conditions is what we've called out here. And you can see we on the green line dashed there, we have two kind of directions that we go here. And this is called out in the PFD that I mentioned earlier, where our first step is a compression step. So you can see we go directly up, increasing in pressure to where we're happy with that liquefaction to occur. And at that point, then we cool the CO2, which is still in gas phase, until it reaches that vapor liquid equilibrium line in blue there. And that's where the liquefaction will actually start to occur, and that CO2 will condense into liquid droplets. And you can see the CD outline there. Cryogenic distillation is typically about where cryogenic distillation targets, but that is a design consideration. So even if we were using the same technology for cryogenic distillation, they may have different endpoints, maybe a different temperature, maybe a different pressure that you may see as your product conditions. It's also very similar to the multi-stage compression, which you can also see in blue, getting towards the critical point there, because there's a lot of variation in the pressure that you can have for liquid CO2. We often see that there's no one standard as to the product conditions that we see in liquid CO2. And of course, there's quite a bit of section in that graph where liquid CO2 can be, but in general, there's not a significant reason to cool it or compress it beyond what's needed. So typically, when you're looking at liquid CO2, you won't see conditions too far away from that liquid vapor equilibrium line. So in general, compression is needed. You can see if we stay at a 1 bar pressure and we just decide to cool the CO2, you're not actually going to hit liquid phase. You'll actually just go straight to solid phase with sublimation. So some compression is needed. You can do it all through compression, or you can do a combination of compression and cooling. Typically, we see compression is more energy intensive than cooling. There's more work going into the fluid there. And also what we see as a science of mixtures is that as you lower the CO2 content in your stream, so as you see more impurities, that actually changes this graph a little bit to where more energy is required. So you see that blue liquid vapor equilibrium line start to increase or go upward or to the left, the dynamics of that change. So something to consider as you look at your tail gas stream and some of the composition aspects of that. You know, what compositions do we have in our stream, and that may affect what work is needed to get that CO2 to liquid. And in general, research supports that as you have your target CO2 parameters in liquid phase closer to the triple point, or you can see on the left there, there's lower energy intensity required, as opposed to the critical point. Typically it involves more energy intensity, and that is just at a high level.
Perry, one thing while we're on this slide that I'd like to add, you discussed how, you know, if you just were able to cool it and cool it and cool it, eventually you'd go straight into the solid phase. And by the oversimplification in the green dotted line on the graph, it may be assumed that you could just compress it straight vertically and get it to fall out as liquid. That isn't necessarily possible just because of the inherent heat increase due to compression. And so you'll see in a lot of CO2 sequestration projects, they'll just compress all the way into a supercritical state and then inject into the ground supercritically. But in any case, for CO2 liquefaction, some combination of cooling and compression will be required. And then, as mentioned, liquefaction can occur anywhere on that blue line. So it's essentially up to the design methodology of the company speccing the equipment, how they want to operate, and where on that line they want to fall.
Yeah, thank you for bringing that up. And good that you bring up the idea of CO2 sequestration. I know that that has been a discussion point in the CO2 market. And there is a reason that we haven't been highlighting that as much, which plays more to the commercial aspect of this CO2 business case. So that's the thing that will be touched on a little bit more in our next installment, just as a teaser here. And we do have a quick animation just to show you all what that process looks like. Just highlighting again what I called out here, starting at that tail gas ambient roughly. So every gas is different. You'll go through that compression phase, and then you go through that cooling phase, your liquid CO2 there. All right. For now, we're actually going to take a quick aside away from some of the cryogenic considerations that we're talking about to discuss CO2 capture versus CO2 recovery. Now, this language starts to change just a little bit compared to what we're used to in the RNG industry, which is why we wanted to take some time here to discuss this. Because when we talk about CO2 recovery, as you see on the upper right hand of the screen, this is effectively a first pass percentage of how much of the CO2 coming into the CO2 liquefaction system, so that dark blue box you see on the screen, how much of that inlet CO2 is actually being liquefied in a first pass. So you can see that's typically seen as your stream 4, your liquid CO2 product, as a function of your incoming tail gas stream, the CO2 content in there. And that does differ from what we see as a CO2 capture rate. And this looks at the plant a little bit more holistically as how much of the CO2 produced in the biogas, so how much CO2 in that biogas will actually be liquefied there. So you can see that lighter blue box is a little bit brighter, or bigger, excuse me. It encompasses more of the plant because there are some different dynamics that you can include within this capture rate. And I would almost consider this capture rate closer to the term that we use when we talk about methane recovery in the RNG industry, where I mentioned that PFD a few slides ago had the RNG upgrader with the 3-stage membrane, and how that 3-stage membrane did have some recycle process included in there to maximize the recovery of the methane, as many of us are familiar with there. And you can see here this gray stream 5 coming from the left side of the CO2 liquefaction side. We see that as our non-condensable gases, which often include maybe a little bit of that CO2 that didn't quite get liquefied in that first pass. If we go straight left, you can see we can just vent that to the atmosphere if that is what the business case maybe dictates or drives to. But we could also potentially recycle this back to the biogas source, as I mentioned on that PFD slide a few slides back, to recover both the methane slip that you may see going into your CO2 liquefaction system, as well as any CO2 that's not liquefied. And so with that recycle stream, you'll see quite a high capture rate, actually, and potentially up to near zero emissions for some of these plants, similar to what you would see with an RNG recovery or methane recovery, where we'll see some systems and technologies upwards of 99.5% methane recovery. So closing that loop increases the capture rate, but doesn't necessarily affect the recovery rate, because that is just a first pass consideration between streams 3 and 4 that you see there.
Very well, we're on this slide. We've got one question in the Q&A and then a couple of points I'd like to make. Question is recovery rate or capture rate more important for the business case? Again, not trying to steal too much from the next installment where we do a deep dive into the business case, but just to briefly discuss here, essentially for the business case, you want to be looking at that stream 4 in a mass flow sense, right? How many kilograms or tons per hour, per day or per year you're producing. Recovery rate and capture rate are very closely linked with one another. As recovery rate increases, your capture rate might not, but both play into the volume of that stream 4. Essentially, if you look at stream 5, if it is recycled, you'll have a greater volume at stream 3, which recovery rate staying the same would increase the volume at stream 4. So your CO2 production, in that sense, is what's really important for the business case. The two big notes I want to make here are, one, the recycling of this non-condensable stream, or stream 5, does really get you close to not only a near zero emission plant, but importantly, near zero methane slip, right? You might have a GC or some sort of a sampling for analysis, and there's an allowable limit of 30 ppm, I believe, in the CO2 product. And so beyond that, there's some periodic venting or burping of that non-condensable stream that is required. But otherwise, you're recovering all of that methane. So for projects with, more than that 0.5% methane slip, it can be a very big add for the business case. And as well, on the CO2 side, your capture rate is almost always dictated by the allowable limit of CO2 in the grid spec for the RNG. So you really get to milk everything out of both sides of the business case when you recycle that stream, if possible.
Yeah, and that brings up a great point for the added value of the CO2 capture and utilization, this liquefaction process that Alir highlighted there, that you're not only creating this CO2 product where you can monetize and add that revenue stream to your plant, but you're also recovering that methane that would have been lost with just the biogas upgrader alone to be able to maximize your value of RNG that you're producing. And an important topic that I actually didn't have in my notes, but I'll just briefly touch on here, is some of the flow considerations that we look at here as we're talking about flows and these calculations. The CO2 flow in stream 4, because you're not a gas anymore, you typically won't see a volumetric flow, a unit, like you would for RNG and most units that we're familiar with, SEFM, MMBTU, or even cubic meters per hour. Because that's a liquid, you typically see that as a mass flow. And so you'll see later on, we reference different masses, mass flows, and that is because that product does end up as a mass. So you make it a little bit more difficult to quantify as a volume flow. It's a little more apples to apples to compare as a liquid flow, mass flow. So that's typically the language that we use here. Just jumping into this next slide here, kind of going back into the considerations of cryogenic processes here. I know we've touched on the contaminants a little bit with these non-condensable gases. As you can see, quite a few of those listed here with the methane, nitrogen, and oxygen. I just wanted to highlight the condition of some of these contaminants that we may consider and what that looks like in a liquid CO2. So if we didn't remove these from our process, what does that actually look like as we saw in the phase diagram, as we compress and as we cool the CO2, what happens to everything else? So you can see methane, nitrogen, oxygen, those all have fairly low boiling points, condensation points. So those will actually stay in the gas as we get this cold. You'd have to go quite a bit colder or quite a bit higher pressure to liquefy those, as some of us may be familiar with the LNG process. But as I mentioned earlier, these are all inherently removed in the distillation process, at least with our technology that we deploy with cryogenic distillation. Moisture, as you see on the top row there, is a little bit different because at these conditions, it will actually turn to solid ice. And so that's why we deploy the dryers that you saw on that PFD slide earlier, because if the water did go into the cryogenic distillation process, it would actually freeze into solid ice, and then you start gumming up your equipment and causing operational issues in that regard there. I also wanted to highlight some contaminants we even consider as contaminants in RNG and biogas, VOCs. Typically, those can be because of the variety of uses that we'll see. We see a variety of different phases that you'll see in the liquid. Some of them are gaseous, some of those are liquid. There's different chemical interactions that may trap them within the liquid if they are supposed to be gaseous and such. So typically we try to remove those in pre-treatment before we even get to our compression process. And this is partly due to wanting to protect our equipment. For example, siloxanes are a key contributor to degrading equipment, as that can turn into ice in your compressor, for example, and degrade that compressor very quickly. So just wanted to highlight some of these contaminants that are maybe fairly common in these CO2 tail gases and where we're going to look at removing them in our process here. Now, just to expand on some contaminants, we go from quite a small table to quite a large table here. We're talking about product purity on this slide. So we've been talking about beverage grade and alluding to that a bit. And as you can see, these allowable limits that you'll see on this product purity are pulled from the ISBT Food and Safety Guidelines back in 2021. And you can see it's not just maybe 4 contaminants that were considered in, considering for that product purity. It's quite a long list, and even some of these are more general. I would call them umbrella terms, like the oxides of nitrogen, for example. I think that's the 4th one down. Kind of an umbrella term for quite a few compounds going on there. So there's quite a bit of measurement necessary for this. You can see even the aromatic hydrocarbons down below needs to be down to a ppb level, part per billion level. So quite a strict requirement on many contaminants here. I think we can all feel a little comforted in that because this is going into beverages that we're drinking, our canned carbonated beverages. So we want that to be pretty controlled there. But it does mean that as we're producing the CO2, we have to consider that if we are wanting to target beverage grade offtake as our CO2 monetization, for example. Now, jumping into the next slide here, continuing on our cryogenic considerations, I believe this will be our last slide touching on the cryogenic aspects of the process. We have the refrigeration, because in this cooling process, you need some sort of refrigerant to be able to cool lower than the ambient pressures and conditions that we look at there. And as we're all, I think, fairly familiar with in many refrigerants used throughout many industries, I've listed a few here as examples just to show, for example, freons. There's many different types of freons. I've highlighted one specifically as an example, commonly used. Those typically have pretty high global warming potentials, that GWP column on the right hand of the screen there, which is why you're actually seeing a lot of these start to be banned for industrial processes. So they're not able to be used anymore. So there's some redesigns that have had to be done for industrial refrigeration systems. Some of these are toxic, which is another consideration you have to consider as well. Some of them aren't. So there are quite a few considerations when it comes to freons there, which is why we're actually seeing a lot of the industries for refrigeration are starting to move away from freon, especially when we look at CO2 as our product that we're liquefying. We typically see down at the bottom that ammonia and even carbon dioxide itself are used as the refrigerants to liquefy CO2. And you can see a large driver for that is the global warming potential. Both of those are fairly minimal compared to some of the other refrigerants you may see. And then the other consideration of toxicity can play into that, can play into your site design. So all of these are different considerations that you want to take into account when you look at your refrigeration process and cryogenic processes in general. Now, this is something you'll have to consider if you're looking into LNG as well. Again, you're going cooler than ambient conditions, so you'll also have some sort of refrigeration process there too. So some of this will be applicable, but of course, with the different end conditions, maybe a colder temperature for LNG, you may see different refrigerants used with higher cooling capacities. Now that wraps up some of the cryogenic considerations that we are discussing, mainly focused on the process side of things. Here we're going to touch on some of the logistical aspects of things, kind of the tail end of the process for storage once you have your CO2 liquefied as a product, and then the transportation in the next slide. We'll talk about that, as I know we touched on that in the first installment of our webinar series as well. But generally, for on-site storage, we see two different types of storage tanks that we'll find. We'll see foam as an insulation method for tanks, and we'll also see double wall vacuum as insulation methods. I would relate this very similarly to water bottles, as funny of an example as it is, but these technologies are fairly robust and very universal for insulation. And we see that in the industrial market and cryogenic market, that double wall vacuum insulated tanks are the standard, very similar to what you'll see if you go into Target and look at the water bottles there. If they're insulated, a lot of them will be vacuum insulated, because the mechanism for insulation there is utilizing convection heat transfer, which in general has lower heat transfer, so lower temperature increases in the tank, as opposed to foam insulation, which relies on conductive heat transfer, which you typically see a little bit higher heat transfer going through. So you'll see your temperature in the tank increasing a little bit further. And as I mentioned, wanted to touch on the transportation aspect of it. Again, you'll see similar tank setups, but these are mobile tanks instead, as you can see on the screen there. So the cost for transporting, because we are talking about cryogenic processes, it's heavily dependent on the distance that you're traveling, because every minute, every hour that you are sitting in a tank as a liquid product, you are fighting against ambient conditions where the CO2 wants to be in a gaseous phase. And so there's energy required to keep it as a liquid CO2 product to prevent it from gassing off, or you may start to lose product as it gasses off and removes from the liquid phase. Now, just logistically, this is a bit different than the RNG market, where we have quite a robust pipeline network that we can inject into. CO2 pipeline network is not as robust, but there is rumors of building that out in specific locations. So trucking transportation is the general means for transporting this liquid CO2. Typically, one truckload can hold about 22 tons per truckload. So depending on your production rate, as Alira mentioned earlier in our process flow diagram there, talking about capture rate, recovery rate, if your production is quite high, you may need multiple trucks coming in per day or per week to pick up that CO2 to manage your on-site storage and deliver that to your client. And like I mentioned, as it's transporting, you do have some evaporation that's potentially happening. Of course, that depends on your insulation. But in cryogenic processes, I pulled this from a report done on LNG systems, that they see typically 0.1% of that liquid cryogenic process is evaporated per day at 15 bar, which is pretty close to the conditions that we see as our product pressure for the CO2. And another point to highlight, as we're talking about insulation, as we're talking about this heat transfer aspect, warming up product in the tank, is that the hotter your ambient conditions are outside of the tank, the greater the driving force is for that temperature to increase in the tank, and therefore more evaporation happens. Of course, this depends on the insulation quality, like I mentioned. But in general, if you are in a hotter climate, for example, if you're in Florida compared to Maine, you may see a little bit more evaporation covering the same distance or same trucking time in Florida than you would in Maine, because the conditions outside the tank are a little bit more extreme. So something to consider, and that does play into the commercial market just a little bit for the CO2 market, as Alira touched on the first part of our webinar series.
Barry, do you know, is the relationship between evaporative loss rate and ambient temperature, or the temperature delta, is that a linear relationship? Is it an exponential one? Do you have any insight on that?
So that plays into the type of insulation that you have. Like I mentioned in the last slide, you have conduction as a kind of an insulation method, as well as convection with the vacuum double wall insulation. And you have different dynamics for how that heat will transfer. So that does affect how you'll see that transfer rate affected. So typically, from my understanding, conduction sees a more linear path, but that may not be the case for convection. Which has a little bit more dynamics in play. So touching on the last topic that I had on the agenda here, talking about how we integrate these CO2 plants into RNG plants. I know we have many existing RNG plants and more popping up left and right throughout the country here and throughout the world, really. And these CO2 plants are fairly easy to install on an existing site. Of course, if you have the site logistics to support it, it's not a system that you have to fully start from scratch and consider in your immediate design. There are some small tweaks that can be made to integrate these plants into an existing RNG plant. But to cover the big topic I wanted to have on this slide is talking about the different upgrading technologies that are common in the industry and what considerations are needed for adding on a CO2 capture plant to those systems. So you can see we start with the Bright PurePack upgrader, our standard technology, as we saw in that PFD near the beginning of the presentation. That is a 3-stage membrane system. So membrane systems in general will be in that column that you see there. Fairly minimal pressure is what we see from those. Close to ambient temperature, maybe a little elevated as we list here, with a low dew point, at least with our membranes that we utilize from Biogenic. Those can remove water fairly effectively. So we see a low dew point, and we see pretty high CO2 purity. You can see 99% or even greater in some cases for that tail gas stream. So typically that's what our standard process can be designed for as a minimum. So it can be fairly easily bolted on to an existing membrane upgrader. Now that changes a bit when we talk about amine scrubbing, upgrading, and PSA upgrading, where you can see the temperature is a bit elevated in those processes. And we also see that the dew point is high and is actually saturated. So the relative humidity of those streams, typically you'll see at 100%. So you have to remove that moisture, quite a bit more moisture than you would for a membrane upgrader. The CO2 percentage, I know we've talked about a lot with those contaminants and what that looks like. Those differ between the technologies, of course, as you can see in those respective columns. But typically, the moisture and the temperature is what we need to consider as we liquefy the CO2. As I mentioned, with the constituents and the other contaminants, a lot of those are inherently removed in the process. So the PSA upgrader, as you see, 90% CO2, maybe a little bit lower quality than the others. A lot of those contaminants will be inherently removed in this liquefaction process, but our standard technology can be applied to those technologies as well. There's no restrictions to those, just some extra considerations to take into place with removing that moisture and cooling that gas. We do have a buffer vessel with an asterisk on the PSA upgrader as maybe something that's necessary, which does depend on the PSA upgrading technology, because these CO2 systems typically like to operate at steady state as much as possible without various swings in the incoming flow rate, just to keep that compressor steady and happy. Then on the right-hand side of this graph in green, I also wanted to call out our other technology, which is our flue gas carbon capture technology. You can see is fairly similar to what an amine scrubber would produce in this tail gas. And likewise, similar technology is required in addition to this base scope PFD that we showed earlier in the presentation.
Terry, while we're on this slide, we've got a couple notes in the Q&A. One comment that a standalone PSA upgrader can typically see CO2 purity as high as 96 to 99% on an AD application. I think important to note here as well for older PSA systems, significant amount of PSA systems in the landfill space and even some 2-stage membrane systems. If you do have an operating site and you're looking for CO2 as an add-on, it's a good idea to target tail gas streams that have 90+% CO2. And in many cases, it's not uncommon to see CO2 streams from tail gas even further south than that. So a good tidbit of information there as you're approaching projects. And then another one, asking for a bit of clarity on the slide. If we're saying we need an amine scrubber and or PSA upgrader added as a part of the bolt-on LCO2 to an RNG upgrader. This slide is the 3 columns in blue, our bright upgrader compared to amine scrubbers and compared to PSA upgraders. Essentially, what would the integration of CO2 liquefaction look like? So for the bright upgrader, that bottom row, we don't need any additional scope to bolt that on, or just to be transparent, any 3-stage membrane upgrader with high quality CO2 as a tail gas, you can essentially pipe it up, manage the controls, and away it can go. For an amine-based biogas upgrader, the CO2 stream is typically saturated, and so we will cool that to remove a bulk amount of that moisture before going to the dryers within the PFDs showed a little bit earlier in the slides. And then for PSA, we're referencing that for PSA upgrader, adding on the CO2 liquefaction might need a buffer vessel, but we'll also need that moisture removal / cooling step.
Yeah, thank you for clarifying that earlier. And to touch on that PSA upgrader, as we're talking about lower CO2 purity streams, just to kind of call back to the conversation we had earlier regarding methane slip, depending on the site, this maybe contaminants, these non-condensable contaminants like methane, could be recycled back into that biogas source or that landfill gas source. So that can be captured and utilized. So even if you have a lower CO2 purity stream here, maybe your methane slip is a bit higher on your site, that can be captured and utilized. And sometimes that significantly contributes to the business case for adding on the CO2 aspect, really just to drive home the value added for the CO2 system, not necessarily just adding another revenue stream, but also maximizing the existing revenue stream you have with that RNG plant.
Right, and to piggyback off that a little bit, let's say someone does have a 90% CO2 stream or an 85% CO2 stream, and they want to capture that methane as the main driver for the deployment of this type of a system. The recovery rate, as we discussed earlier, recovery rate defined as a single pass of the liquefier, the proportion of CO2 that becomes liquid versus does not. That recovery rate does decrease as your CO2 concentration decreases, as with any sort of CO2 liquefaction technology. And so in instances where you have a low quality CO2 stream or high amounts of methane in that stream, there are alternate scope items that we can add in to alleviate a little bit of that stress on the recovery rate and then provide an overall better business case, better operations. So in one case, we can include membranes to recycle some of that CO2 that is the non-condensable stream and split that stream so that you have a bulk methane stream being recycled up to the upgrader. Or in some cases, it's better to add a single stage PSA. Bright offers in-house PSA technology, and really this is applicable for any low quality CO2 stream, even 20 to 60% CO2 if you've got that type of an opportunity. The PSA can boost the CO2 quality coming into the liquefier upwards of 98, 99% for easier and more efficient liquefaction. So I know that's a lot to throw at you and kind of getting in the weeds of the technical, but just want to make it known that any CO2 stream essentially, regardless of the quality, can be recovered. And in many cases, recovering the methane is a significant and even sometimes a strong enough financial driver to do the entire scope of the project.
Yeah, thanks for bringing that up, Alir. I know we're starting to get close to the end of our time at the 50-minute mark here, so I want to keep things rolling. Jumping into our last slide, which relates to the last column that you see here, deviating a little bit from the RNG plants as we talk about here, but I know before RNG plants, there are many power generation plants using CHP engines or anything similar to that. And we do have technology and we have seen applications for CO2 capture and liquefaction there as well. So what you see on screen here is a very interesting layout for a project that we have recently commissioned in Austria, where we are capturing flue gas from an RDF plant and liquefying that CO2, extracting that from the flue gas, liquefying that CO2, and producing food and beverage grade quality CO2 that will be going into beverages, which just drives home the point that this CO2, this biogenic CO2 that we're talking about has a lot of value that can be put into these existing food and beverage industries. And whether we're producing biogas, whether we're throwing it into an engine and have flue gas, we can capture this. We can decarbonize our exhaust streams and capture this waste stream. In my opinion, that was the whole basis of the RNG and the biogas industry, was to capture these streams that are typically seen as waste and to utilize it and make a business out of that. And this is an extension of that same mentality and process.
One fun fact while we're looking at this, this particular project is capturing CO2 from a wood-fired boiler. And for anybody that might be interested, woody biomass burning projects in the States has a really strong, I believe, upwards of 40% ITC. So if anybody's interested in making a CO2 project happen, that might be a good avenue to explore, especially with the amount of woody biomass that we have available in the US.
Yeah, and if that is the case for you, we'd be happy to maybe talk to you about this project a little bit more so you can learn about how we actually put this into practice here. But that's what we had for our content today. We appreciate you all sticking around and bringing your ears and your questions here. Feel free to reach out to the Bright Boys, as we've deemed ourselves. You can see our contact info on the screen there to reach out if you want to learn more. And like I said at the beginning of this, we will have the recording posted if you do want to rewatch, relearn, and be able to ask your questions later on as well. But Dylan and the RNG Coalition, we appreciate your time and availability in this platform to be able to give this information.
Yeah, the Bright Boys, I love it. I love the super group vibe we've got going on here. Great stuff. I really appreciate that. Covered a lot of territory here in about 50 minutes. I'll give one last chance. I see someone else asking thank you, and thank you to all of our attendees as well. I'll give you one question here. Maybe, I teased at the top, we're thinking about doing a third installment in this series. Can you maybe give a quick preview on what folks might expect? We don't have a date yet, but just next time they see Bright on the calendar, they maybe can know what to expect.
Right. So quick preview without getting lost in the weeds here. It's a little bit long of a deck. I've already got it made. We'll be covering kind of zoning in on food grade and beverage grade and exploring what does a business case look like? What do the specs look like and where do they stem from? Some financial modeling terms and maybe how to approach a financial model. The idea I touched on earlier of cost offset to the consumer. I'll share some consumer perspective and insights just to bridge the gap in understanding, talk about the current state of biogenic CO2 and how it relates to the market, some contractual considerations, value drivers. I mean, the whole nine. So everything you can look at all the way from what the spec is to some insights to realizing the project.
Fantastic. Thank you for running that down. And you can look forward to seeing the Bright Boys again soon. Keep an eye on your member weekly for the latest in if you are an RNG Coalition member and you're attending this webinar, keep an eye on your member weekly. Otherwise, keep an eye on our social media accounts, especially on LinkedIn for upcoming Wednesday webinars. I can tell you our next one scheduled is with Pillsbury Winthrop Shaw Pittman, the law firm, for a presentation entitled Navigating Financial Distress, which is going to focus on, how companies within the RNG industry that maybe have had a turbulent 2025. It's been an interesting year and an interesting market, as it has, I think, across all commodities and many different industries, frankly. And they're going to be focusing on ways within the RNG industry specifically that firms can navigate financial distress, and I believe partly using tax credits and different tax equity structures. So stay tuned for that on October 29th, back here at the same time, same place. And otherwise, once again, thanks to our friends at Bright Renewables, and I'll wish everyone a safe and happy day. Thanks for joining us. Bye, everybody.